Okay, circular motion. If we consider a stone tied to a rope, okay, this is the length of the rope and this is the stone that is tied to the rope. By the time the stone is here, the velocity of the stone will be tangential. The velocity of the stone will be tangential to the circular path. By the time the stone gets to this point, the velocity of the stone at this point will also be tangential to the circular path. Okay, so it's obvious that the velocity of the stone is changing as the object, the stone in this case, covers some angle. Okay, as it makes some angle turned, the velocity of the stone is changing. Okay, so if the velocity of the stone is changing in direction, don't forget velocity is a vector quantity, okay, and so it has both magnitude and direction. If the velocity of the stone is changing in direction, therefore we can write that for the velocity of the stone, we can write that A is equals to V squared divided by R. Don't forget, my A is the acceleration of the stone, okay, then V is the velocity of the stone, and R is the radius of the circular path. Okay, so if I'm to call A the full name, A is centripetal acceleration. A is called centripetal acceleration. Okay, and is always directed towards the center of the circular path. As that acceleration is always directed towards the center of the circular path. Okay, so in this case, this will be my R. Okay, and the direction of my A at any point is towards the center of the circular path. The acceleration of my A at any point is towards the center of the circular path. So if an object is performing circular motion, just as the stone I just described to you, it will have a centripetal acceleration. And that acceleration is directed towards the center of the circular path. All right, because it has acceleration, it will also have a force. Okay, and don't forget, force F is equals to the product of mass and acceleration of a body. Product of mass of a body and the acceleration of a body. Okay, so if I'm to substitute this A into the formula for force, and we have F is equals to M multiplied by V square divided by R, where R is the radius of the circular path. My R is the radius of the circular path. All right, so from there I can write that my F is equals to mv squared divided by R. My force is equal to mv squared divided by R. Now take note that this force is called centripetal force. This force is called centripetal force. This type of force is called centripetal force. So the force that makes an object to keep moving along a circular path is called centripetal force. All right, having said that, we can move on to derive some equations. Okay, all right. Now, what about the centrifugal force? There's also another force that is called the centrifugal force. What about the centrifugal force? How do we calculate and get the centrifugal force? The centrifugal force is a force that is equal to the centripetal force but acts in the opposite direction. So if I'm to write for my centrifugal force, F, centrifugal force F is equals to minus mv squared divided by r. Okay, this is my centrifugal force. Okay, so the centrifugal force F is equals to minus mv squared divided by r. That is to tell us that the centrifugal force is equal to the centripetal force but only acts in the opposite direction to the centripetal force. If I'm to calculate the angle turn, let's go back to the diagram of the circular motion made. For this circular motion, if I'm to get the angle turned, I want to make a derivation for the angle turned. This angle, the angle turned here. All right, so what will that be? Okay, I want to make a derivation for the angular velocity. Okay, in terms of the angle turned, I want to make a derivation for the angular velocity in terms of the angle turned. What will that be? Just like my linear velocity is equals to angle turned. Linear velocity is equals to distance divided by the time taken, displacement divided by the time taken. Also, my angular velocity is equals to angle turned divided by time. The angular velocity is the angle turned divided by time. Okay, and then I said this is angular velocity. Okay, that's angular velocity, which is angle turned divided by time. But recollect that my linear velocity v is equals to displacement divided by time. Okay, so this is linear velocity. Okay, linear velocity v is equals to displacement divided by time, but the angular velocity is the angle turned divided by time. All right, so I haven't said that, but if the angle covered by the object that is performing circular motion, is small, let me show you that. The angle covered by the object that is performing circular motion, that is this angle, if it is so small, as the object moves from point A to point B, it's going to go through arc S. Okay, so it will go through arc S, okay, from point A to point B. It's going to go through arc S. All right. So if I'm to write the angle turned in terms of this arc S, okay, which is the distance the stone is going to pass, the path along which the stone is going to pass to get to point B, that will be equal to theta is equals to S divided by R. Okay, theta is equals to S divided by R. Okay, so from here I can make S the subject of formula such that I will have S is equals to theta R or R theta, anyone you prefer to use. S is equals to theta R or R theta. Okay, so if I substitute this into the formula above, I can write that V is equals to theta R divided by T. Okay, V is equals to theta R divided by T. But theta divided by T looks like what I know before. Okay, that looks like what I know before, and that is what my angular velocity. Okay, so I can write that V is equals to omega R. V is equals to omega R. Okay, it's the same thing as writing V is equals to R omega. Okay, so this is a formula that connects the linear velocity V of an object that is performing circular motion with the angular velocity omega for an object that is performing circular motion. I hope you understand. See you in the next class. Thank you. Let's draw the diagram for another object that is performing circular motion. This is the diagram for another object that is performing circular motion. Okay, such that this is the object. In this case, the object is here. Okay, this is the object that is performing circular motion. Let me divide the circle into quadrants. Okay, I divide the circle into quadrants such that this is the radius of the circle. That is the radius of the circle. Okay, and if I draw a perpendicular from where the object is to this line, okay, I draw a perpendicular as that. This will be my x, where x is the distance from this point to this point. Okay, x is the distance from that point to that point. Okay, so this is Q. Let me call this place Q. I call this place Q, and let me call this place C, which is the center of the circle. Okay, so the linear velocity V at any point Q, whose distance from C, the central point, is x, is given by. So if I want to get the velocity, the linear velocity of this object. Okay, if I want to get the linear velocity of this object, all right, that has x distance, okay, x horizontal distance from the origin, from the center of the circular part, I will use the formula. V is equals to omega square root of a square minus x square. V is equals to omega square root of a square minus x square. Okay, all right, what about if I can quickly get the adjacent from our SOHCAHTOA? I can write that if this place is theta, let's go back to the diagram. If this place is theta, okay, that is the angle turned is theta, what will be my cos theta? Cos theta will be equal to, adjacent divided by the hypotenuse. Okay, cos theta will be equal to adjacent divided by the hypotenuse. Okay, so in this case, my cos theta will be equal to adjacent, that will be my x, divided by the hypotenuse. The hypotenuse is my r, okay? But take note that my r, which is the radius of this circular part, is also equal to my a, which is the amplitude in simple harmonic motion. My cos theta, which is equal to x divided by a, is also x by cos theta, which is x divided by r, where r is also equal to a, which is the amplitude, okay, of the object that is performing simple harmonic motion. Yes, we can relate circular motion with simple harmonic motion. Okay, so I can write cos theta is equals to x divided by a. All right, so if I cross multiply from here, I can write that x is equals to a cos theta. I can write that x is equals to a cos theta. X is equals to a cos theta. Okay, so from here, I can then do something. If you don't forget, I've already obtained a formula for my theta before. Okay, so I got my angular velocity is equals to angle turned divided by time. If I cross multiply, that will give me theta is equals to omega t. Theta is equals to omega t. So if I substitute into the equation above, I can write that my x is equals to a cos omega t. I can write that my x is equals to a cos omega t. All right. Having said that, let us differentiate our x with respect to time. Okay, let's differentiate our x with respect to time. Okay, so differentiating x with respect to time, we can write that the x divided by dt is equals to dx divided by dt is equals to, okay, so that will give us omega will come out, okay. Then I will write this constant, which is a. By the time I differentiate cos, it will give me minus sign. So I'll put minus sign. Differentiation of cos will give me minus sign. Okay, then I will put omega t, that is in front. Okay, so don't forget, differentiation of omega will come out. All right, since I'm differentiating with respect to t, omega is what is at the back of t under sign, so omega will come out. Differentiation of cos will give me minus sign, that is the reason for the minus. That is how to differentiate our x with respect to t. That is what we get when we differentiate our x with respect to t. Okay, but don't forget, when we differentiate displacement with respect to time, what we actually get is velocity. Okay, so I can write that velocity is actually equal to dx dt, okay, which is equal to minus omega a sine omega t. Okay, so actually what we get when we differentiate this distance or displacement with respect to time is the velocity. All right, let's differentiate one more time. Let's differentiate this one more time. Okay, that will give us, if we differentiate that one more time, that will give us d square x dt square. Okay, so if we differentiate one more time, that will give us d square x dt square, which is equals to, in that case, that will be equal to minus, we come out again, we have minus there, then omega will come out again, making omega square, then a, then cos omega t. Okay, minus is there because of the minus that we have up there. Then I will have omega square, okay, and then I will have my a, which is the amplitude, then cos omega t, if I differentiate one more time. All right, but take note that this actually is where we are coming from. A cos omega t is our x, which is where we are coming from. So that tells us that d squared x dt square is equals to minus omega squared x. D square x dt square is equals to minus omega squared x. Now, when we differentiate displacement twice as this, when we differentiate displacement twice as this, what do we have? We have velocity, we have acceleration, we have acceleration. Therefore, my acceleration a is equals to d square x divided by dt square, which is equals to minus omega squared x, which is equals to minus omega squared x. Okay, so this actually is what we have when we differentiate our displacement twice. When we differentiate displacement twice, okay, all right, and that gives us the acceleration. How to get the acceleration for an object that is performing simple harmonic motion. Don't forget that it is from the circular motion that we have been able to enter into simple harmonic motion. All right, so can we see the relationship now? Can we see the relationship between linear velocity and angular velocity? Okay, can we see the relationship between linear velocity and angular velocity? All right. Okay, let's see the relationship between linear acceleration and angular acceleration. Let's see the relationship between linear acceleration and angular acceleration. Okay, so for angular acceleration can be defined as angle turn, change in angular velocity divided by time required for the change. Change in angular velocity divided by time required for change. Okay, so if I'm to define angular velocity, we will define it as change in angular velocity divided by the time required for the change. Okay, so I've written that we can write that our angular acceleration is equals to final angular velocity minus initial angular velocity, just as we do for linear acceleration. That is final velocity minus initial velocity, then divided by the time taken. Okay, but take note that my angular velocity omega is equals to linear velocity divided by the radius of the circular path, okay, which is the same as V is equals to R omega, just as we have written before. We have used it over time. Okay, so from this we can write that, okay, we can write that angular velocity is equals to V divided by R, okay, minus V naught divided by R. Okay, so from what we have at the top, then everything divided by T, all divided by T. Okay, so if we factorize R, we have 1 divided by R, open bracket, V subscript T minus V subscript V naught divided by T. Okay, so we have that as the formula for our angular acceleration. But take note that this same V minus v naught is also our linear acceleration. Okay, so this, our linear acceleration, is equals to v final velocity minus initial velocity divided by the time. Okay, so I can write that 1 over r is our a multiplied by our a, which is also equal to a over r. Okay, so my angular acceleration is equals to linear acceleration divided by r. Okay, so if we cross multiply from there, I can write that linear acceleration, angular acceleration, is equals to linear acceleration divided by r. Okay, and if we cross multiply, that will give us a is equals to angular acceleration multiplied by r. That will give us a is equals to angular acceleration divided by r, where a is linear acceleration. This is angular acceleration. Please take note of that. See you in the next class. Bye.